Hello. It's 11:30 p.m. where I am, but I took a giant nap, so probably not gonna be able to sleep before work tomorrow, which is the day of the paper one exams. So I figured I might as well just finish off the last of the HL papers that have come out. And so I'm doing November 2021 time zone 0 paper 3. And I don't know, like I said before, paper threes are generally heavily guided and they just kind of make you do stuff and find out stuff. So why don't we just start? And I don't know, is there a point to doing these? Because each paper three is going to have a different question that's going to be like not even related to the former paper threes. But whatever, I'll just do them anyways. Alrighty, we are going to explore special functions. So here's the first one, here's the second one. Z can be complex numbers. T, E, U, and are real numbers. Verify that U, being f of t, satisfies this differential equation. Okay, so they're saying that the second derivative of u should be equal to u itself. So I don't know, I guess we just take the derivative of f twice. So what is this going to be? F prime is e to the z minus e to the negative z divided by 2. F double prime is e to the z plus e to the negative z over 2, which is equal to f. I guess I should call it u for the sake of consistency, but okay, that's pretty easy. So u. Okay, next up, show that f squared plus g squared equals f of 2t. Okay. So if I am going to take this one and square it, probably not enough room there. Now let's just write it again. Okay, add these together. Okay. I guess I'll square these. So I have 2z plus 2e to the z e to the minus z plus e to the negative 2z over 2. Well, that's 4. And then, okay, whatever. I'm just gonna write it down here. I need more room. Okay, add that to the exact same thing, but with some minuses in there. Okay. Anyways, these cancel out when you combine the like terms in the numerators. So you're gonna get 2e to the power 2z plus 2e to the power of negative 2z divided by 4, and then basically you can divide a 2 out from everything. So you will get e to the 2z plus e to the minus 2z over 2, and then this is equal to f at 2z. But oh, we're supposed to use t, but same thing. Okay. Now, using e to the power iu is this stuff, complex numbers. In terms of sine u, cosine u, find out f of iu, sure. Okay, so plug in iu, and then we use this identity right here, which is just changing from Euler form to polar whatever form. So this is cosine u plus I sine u plus cosine u minus I sine u all over 2. And then cancel, cancel. And then you'll basically have a 2 cosine u divided by 2 when we add these together, and then divide, divide. So this is just cosine u. Okay. And then I think g was just doing the same thing, right? So the only real difference is there's a minus in between. I guess that's going to change a couple of things. Okay, if this is minus, then this is going to be minus and this is going to be plus. And then cosines cancel, and then same concept, if you add these two together, you'll have 2 of them, and then these divide, and so you just get I sine of u. Okay. Hence, simplify and find an expression for f of iu squared plus g of iu squared. Okay. So that's going to be cosine u squared plus I of sine u squared. So we just have cosine 2u, and then basically minus sine squared u. And then do they want you to keep simplifying this? Because this is a double angle identity, I think. So this is cosine 2u, I think. I don't know. You guys have a formula book. If not, then you can stop right here. But if it is an identity, which I'm pretty sure it is, and I'm pretty sure it's this one, but yeah, I don't want to pull out my formula book. Okay, sure. So the next ones, so the functions cosine and x are known as circular functions, blah blah blah, because this coordinate makes the point on the unit circle. Okay, so f and g, they're known as hyperbolic functions. Yeah, they are, yeah. And so when you combine f and g for an angle as a coordinate, they're going to make points on a curve known as a hyperbola. And hyperbola has this equation instead. And they have two asymptotes. So we need to sketch this graph, state coordinates of axis intercepts, and the equation of each asymptote. Yeah. So anyways, yeah, hyperbolas are they're part of conics, which are not part of the IB curriculum. So I'm not going to talk too much about them, but you just want to graph this, right? So if you have a graphing calculator that can graph relations, not functions, then this is very straightforward. So here's x squared minus y to the power 2 equals 1. So this is a hyperbola. And then, as you can see, it has x-intercepts at -1 and 1. And then it has two asymptotes. They are oblique. There's one here at y equals x. And there's another one at y equals -x. Okay, now if you don't have a calculator that can do relations, then what you need to do is you just need to basically isolate for y so that you turn it into a function. So for this one here, we know that y squared is x squared minus 1. And then obviously it's a relation, so when we do isolate for y, and we do the square root, there's going to be the lower half and the upper half. And you will need to graph both or just reflect one of them to get the other. So this will give you the upper half, for example. Right, this is the positive half. And then you can reflect it or regraph it or graph a second graph with the negative part. Okay, so then sketch asymptote intercepts at 1 and -1, and then label any asymptotes. So there's one right here at y equals x, and then there's another one right here at y equals -x. And then your graph goes pew, 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 pew. Okay. So the hyperbola can be rotated, okay, to coincide. So coincide means like you turn it and then I guess it overlaps with this curve, xy equals k. K is a number, find the possible values of k. Okay. So like I said, if you do have like a graphing calculator that can do relations, then as you can see, you'll get this graph. So if you compare that to the hyperbola graph, you can see that if you were to rotate it around the middle here, over this way or that way, it will kind of overlap, except for now my k value is 1, so we need to adjust this so that it matches perfectly. So how do you do that? Okay, first off, if you can't graph this, then same thing, you can isolate for for y. And then this is pretty straightforward because you should know this from SL content. This is your reciprocal function. and then it's just multiplied by a constant. Okay. So normally y equals 1 to the equals 1 over x is going to be this function right here. And then our hyperbola looks like this. So we need to turn it, I guess, rotate this way. And then I'm going to make this overlap with this. So this coordinate right here is 1 and 0. And then I need to rotate it over here to match this and become this coordinate. Okay. So I should find out what the coordinates are that it will turn into. And the way you can do that is a little bit of Pythagoras. This has a distance of 1, which means that as you rotate it, let me stay color coordinated. This needs a distance of 1. Okay. And then let me redraw this so that it's larger for you. So y equals 1 over x. It has an invariant point, which is 1, 1. And as you can tell, if you were to do Pythagoras, this has a length of root 2. And we don't want that. We want the length to be 1 because of what I said earlier. So we can transform this function if we want to, so that the x and y values, which are the same, we need them to be a distance of 1. So each one should be 1 over root 2. So this should be 1 over root 2, and this should be 1 over root 2. And then that will give us the correct distance of 1 that we need, so that this point lands and coincides with the reciprocal graph. So what we've done is we've basically transformed our function. We had two transformations. We have a vertical, well, they're both stretches or whatever they're called, scales, stretches. I'm just going to say stretch. Vertical stretch by square root 1/2. This one is a horizontal stretch by not 1/2, 1 over root 2. And so in terms of function notation, what we've done is we've taken, here's my vertical stretch transformation, and then here is my horizontal stretch transformation. And then note that this one is root 2, whereas this one is 1 over square root 2. Okay, and then this is going to help us find k, because k is going to be whatever all of this coefficient stuff is simplified. So we have the root 2 and the root 2 are going to basically multiply and make 2. So 1 over 2x, and then that basically means that k is 1/2. And then it says possible values, so then there's more. Oh, I guess you can take this coordinate and the whole graph right here, and then you can rotate it so that it matches the other section. So this one rotates and matches here. And then if that's the case, then well, if we needed it to become positive 1 over root 2 and positive 1 over root 2, this one is going to become, sorry, this is messy, but hopefully you guys understand what I'm saying. If you want to rotate it to that coordinate needs to be negative 1 over root 2 and positive 1 over root 2. So then your transformations are going to be 1 over root 2 and then negative root 2 over x. So we also have negative 1/2 as a possibility. Yeah, so when k is 1/2, then as you can see, this point can rotate to right here, and then it's the appropriate distance of 1 away, so then they coincide. Or if you do negative 1/2, oh, then it just rotates. Oh, then the reciprocal graph changes, but now it just rotates this way. Or you can think of this one rotating all the way over here. Yeah. Oh, I had it slightly backwards, but it's the same thing. I made the hyperbola negative or whatever. Anyways, you get the same answer. Okay. Oh, and then we're done. All right, what is this? Exploring a system of linear differential equations. Okay, let's see how far they take this. Anyways, there's lots of ways to explain this, by the way, especially if you've learned conics and hyperbolas. But I think the way that they're guiding you, this is probably, excuse me, probably the easiest way to explain it. All right. So we have a linear system of differential equations. Sure. First, consider the case where a is 0. If a is 0, then in our second one, we just have dy dt equals y right here. And then show that this is a solution where a is a constant. Okay, that's easy enough to do. Dy dt equals y. I don't know why I wrote it again. We use a separation of variables. This is your pretty standard stuff for HL. So you get 1 over y. Dy is equal to dt. Then you can integrate both sides. And then you'll get natural log of y. It's actually natural log of absolute value y, but they do tell you that y is going to be a positive number. And then this is equal to t plus some constant. and then we solve for y. So basically this is saying that e to the power of t plus c is equal to y. And then if you're adding exponents, you can write that as a multiplication of 2 powers of e. And then e to the power of c is just some number, so then they just change it to a. And then you're done. Okay. Then next, show that dx dt minus x is equal to this. Okay, that's easy enough. We're going to use this one here. So dx dt is equal to x minus y. And then from part A, I know that y is a times e to the power of t. And then this is obviously going to be what you need to show when you subtract x. Okay. Now solve the differential equation in part AII and find x as a function of t. Okay, so they want you to solve this, and then the way that this is formatted, you have to use an integrating factor. Because essentially dx dt plus some function of t times what is this? Some other function of x should equal another function of t. I forgot the formatting, but whatever. If you have it in this format, where this side is just a variable of t, you have your derivative, and then plus or minus some expression of x multiplied with some expression of t, then we can use an integrating factor. So in our case, t is just -1. And then I think the integrating factor is, I just did a video on this, so I should remember it. I believe the integrating factor is e to the power of the integral of the function f. So in our case, this is e to the power of the integral of -1 dt, which is e to the power of -t. And we don't need to include the plus c in the integrating factor. Okay, and then what we do is we multiply everything by the integrating factor. And then more specifically, we know that on the right side, these are going to cancel out. So you get -a. And then the whole purpose of this is that when you multiply e, the integrating factor on this side, what you've done is you've created a product rule. And so we know that this is the derivative of the function g right here, which is just x, times the integrating factor. Okay. And then from here we're solving for x, so I think we can just take the integral of both sides. So you'll get x e to the -t is equal to -a times t plus some other constant c. this is not the same C as the C from earlier. Okay. Hopefully I'm doing this right. And then that means that x as a function of t is I guess I'll just write it like this. Is this. Okay. Now, paper threes are so heavily based on how you do in from the earlier parts. So normally I would check my answers like at the end, but I don't know. That I need to make sure that that's correct. Oh. Okay. Yeah, looks good. All right, moving on. Now we're going to consider the case when a is -1. Sure. So if a is -1, then that second differential equation becomes this. And then you need to show the second derivative is equal to 2 dy dt. Okay, and then what was the first derivative, or the second linear equation? I think it was x. Was it y minus x? X minus y, okay. Okay, so we're gonna take the derivative of this to get the second derivative. That's easy enough to do. So from here, d squared y over dy squared is equal to negative dx over dt. Oh, whoops, this is dt squared. And then plus dy dt. Okay. And then I need to show that this is 2 dy dt. Okay, I'm going to do some substitutions, I guess. So negative x dt, we're going to use this formula right here. So the first linear equation, so negative x dt is the same as minus x plus y plus dy dt. And like, yeah. And then I need to show that this is dy dt because you're supposed to have two of them and this is one of them. Oh, and it's right here. Okay, so this is equal to dy dt plus the other dy dt, which is 2 dy dt. Nice. Okay, by substituting big Y as dy dt, show that big Y is equal to this stuff, where b is a constant. Okay. So I'm trying to solve for Y, and then I'm going to use this right here. So first off, d squared y over dt squared, this is the derivative of the derivative. So this is the derivative of the derivative. So when I make my substitution as big Y is the derivative, then this becomes this becomes a basically first order differential equation. So all we're doing now is we're finding out this equation. First order means it's one derivative and not a double derivative. So this becomes d of dy equals 2y. I think. And then solve this equation. And then you should get this. Okay, easy enough to do, I think. Oh, I guess I shouldn't write it like this. Because then this is a little... Yeah, and then we solve this one. So this is just another separation of variables, just like in part, the earlier part. And then you've seen this before. Integrate both sides. It's just this, where is it? It's just this one again, right here. Oh wait, no, that's the integrating factor. It's just this one right here. And then you'll get big Y is equal to, I guess, some constant B, e to the negative or positive 2 big Y, or T. Yeah. You're literally just following these steps again. Okay. Hence, find y as a function of t. So now I unsubstitute this, I think, because this is dy dt, and then this is equal to b e to the power 2t. And then again, if I want to find the function y, integrate with respect to t. So I should get y is equal to whatever this is, b over 2 e to the 2t plus some other constant, c. Okay, and then hence show that x is going to be negative b over 2 e to the 2t plus c, where c is a constant. Okay, so we're just solving for x, right? So I guess we'll use this equation right here. dy dt is equal to negative x plus y. And then from the previous parts, like right above, I know that this is that. And then I also know that this, which is capital Y, right? And I know that capital Y is this, b. So the left side is b e to the 2t, we have minus x, and then y we know is b over 2 e to the 2t plus c. Okay, so if you solve for x, then you're just going to take b over 2 and then minus b, so that's negative b over 2 e to the 2c 2t and then plus c. Okay, that was easy. Now consider the case where a is 4. Okay, let's just keep going, I guess. Jesus, what is happening? So if the case is 4, then we have, again, dx dt, which is x minus y, and then our new second linear differential equation is negative 4x plus y, I think. Yeah, okay. Hence, show this. Okay, I think we're gonna do a similar process as here, like this. So I'm going to take the derivative of the second linear equation so that I can get d squared y over dt squared. So d squared y over dt squared is equal to negative 4 dx over dt plus dy over dt. And then let's see. I need this in terms of dy, dt, and y. So that means that I should not have a dx dt, but I'm just going to do a substitution. And then we'll see where we go from there. So this is equal to negative 4 times x minus y plus dy dt. So I'll have negative 4x plus 4y plus dy dt. Okay, and then like I said, this needs to be in terms of dy dt and y, so there's no variables of x. Oh, and then negative 4x is right here. So I'm going to substitute it with dy dt minus y. And then I think, oh yeah, that will get us what we need. So yeah, I just subtract this y over here and then do the substitution. Jeez. Okay, so currently we have d squared y over dt squared is equal to, and then on the right side we have these two added together. So that's 2 dy dt, and then plus 3y when we add these two together. And then we're basically done, right? We just need to move everything to one side. This takes me back. So we actually, well, I guess it depends on what university you go to, but this is a differential equation question, and then obviously as a math teacher I've taken courses on this, so it takes me back. Okay, so we basically have this here, and then from previous cases we conjecture that there's going to be a solution for y, and it's going to be in this format. Again, from our previous cases, here and here. So y is going to be some constant f times e to some other constant lambda times t, and then find the two values of lambda that will satisfy this. Okay, so we want to satisfy this equation. and then we are conjecturing that our solution will be in this form. Okay, so we're just going to do a couple of derivatives, and then we can plug them in, and then probably solve for lambda. So I need to find dy dt. So this is just lambda times f e to the lambda t, and then d squared y over dt squared is equal to lambda squared f e to the lambda t. Okay, and then we basically plug these in. Minus 2 lambda f e to the lambda t minus 3 f e to the t equals 0. Right, so I'm just plugging in these values into this equation right here, and then f is a constant that's non-zero. We have e, which to the power of whatever isn't going to be 0, so I can just cancel out all of these things and divide every term by f e to the lambda t. So basically we are solving this quadratic equation for lambda, and such is solving differential equations. You end up just solving quadratics. So lambda is minus 2 and 3. Okay, and then let the two values be lambda 1, lambda 2. Verify that this is a solution to this equation as well, where g is a constant. Okay, so I think we just basically do the exact same thing again, just now with actual values. So y is equal to fe3t plus ge negative 2t. So I need to find dy dx, or not dx, dt. So this is going to be 3f e to the 3t plus minus 2g e to the negative 2t. And then the double derivative is 9fe3t plus 4ge negative 2t. And then we're going to substitute these values into this differential equation right here. So I'll have this thing minus 2 times this one okay, multiplied by negative 2 wait, I'm just gonna, okay, multiply by negative 2, so this is minus 6, this is plus 4, and then take one of these, and then I subtract 3 from them, or well, multiply it by negative 3. So multiply by negative 3, this is equal to 0. Okay, and then if we collect like terms, everything just cancels out, I get, probably. So let's see. We got 9, minus 6, minus 3. So those cancel. we got 4 minus 4 or wait, 4 plus 4 minus 3. Sorry, this this song is throwing me for a loop. I'm gonna switch it. Oh no, did I mess up somewhere? Okay, 4 plus 4 is 8, minus 3 is 5, but I'm supposed to get 0. Ah, so close. Okay. Did I mess up somewhere? Minus 2, so minus 6 plus 4, 3, so minus 3 minus 3. 9 minus 6 minus 3. 4 plus 4 minus 3. Oh well, okay. We'll just see what happens here. I don't know. I don't really want to think about it because it's late. Let's see what happens. Oh shit. I factored wrong. Oh well. Oh my gosh. Why am I so stupid? Okay, obviously factored wrong. Hopefully, for those that are watching, I don't know if you noticed. You probably haven't, but I have because I get the notifications. But watch the whole video before you comment whether or not I made a mistake, because I might catch it later. Okay, so what does that change? That means that these are gonna change. So plus 2, and then this one is times -2, so plus 2, and then derivative again, so it goes back to plus, and then this one, okay, this one is also different. So this is -3, and then this one is just plus. There you go. Okay. So anyways, whatever. My method was right. I just messed up a little bit. So I factored wrong, which means that this is minus t. So these are all of your derivatives. So if you plug them into this equation, now everything cancels out. So pew, pew, pew. 0 equals 0. And I think that's the end of the paper, right? Yeah, it is. Okay, well, I don't know. There's not much to check because, again, a lot of these are just showing things. The only one that we really need to check is this one, possible values of k. Anyways, the second question was fun. It's a pretty typical process for solving linear equations. And then, okay, k is plus or minus 1/2, right? That's what we got. Well, what I got. Yeah. And then, I don't know, this one was okay. I like the first part before they asked you to graph a hyperbola out of nowhere and then asked you to rotate it. This K one is a really tough question. Oh well, okay, there you go. I have gone over all of the past papers of this new curriculum. Granted, there wasn't much. The exam is today, rather, because it's past midnight now where I am. And I'll get a copy of the exam. And I don't know, I think there's like a 24-hour blackout period. And then after that, I could get struck with copyright claims, I think. But I don't care. Just don't report me. Okay, thanks for watching. I'll see you guys later.